Hello, everyone. Welcome to the last panel of the day. This is the life cycle panel. The focus of this panel is to discuss how plastic, water impact each other through the production, use, transport, disposal, and recycling of plastics. I'd like to introduce Lauren Summers, who's a postdoc in civil and environmental engineering at MIT, and she will be moderating the panel and introducing our panelists.
Great, thank you very much. I'm Lauren Summers. I'm a postdoctoral fellow here at MIT. My research has to do with climate change and water resources and the interplay between those things. But today we're talking about plastic. And so thanks for coming to our panel on the plastic life cycle. The goal of today's panel is really to look at an overview of how plastic and water interact throughout the entire plastic lifetime. So from production, use, and transport to disposal and recycling. So we're joined by our four panelists, and I'm going to introduce them from this side over. So first we have Michel Berthiaume. Michel has over 30 years of experience in assisting and financing numerous startups, mentoring a number of entrepreneurs and corporations, and co-founding Oceans United nonprofit organization. He developed and refined a plastic-to-fuel hybrid hydrothermal liquefaction system capable of processing up to 50 tons a day and generating 45,300 liters of sulfur-free diesel fuel from waste and contaminated plastics. He was awarded the Order of Canada Diamond Jubilee Medal in 2012. So thank you for joining us. Next, we have Glenn Flierl. I think I might have got that right. Glenn is a professor of oceanography here at MIT, and his research is concerned with the theory of geophysical vortices and jets, and his interests include modeling the physics, chemistry, and biology of strongly non-linear ocean eddies and meandering jets, such as the Gulf Stream, which meander around their average paths with wave-like features, having many different scales and periods, with the resulting non-linearities playing a significant role in the dynamics. Next, we have David Sanchez, and he's an assistant professor of environmental engineering at the University of Pittsburgh and the assistant director of the Mascaro Center for Sustainable Innovation. And David oversees research for the Sustainable Design Labs, where they look to improve systems on a regional to national scale. His current projects include creating predictive water quality and quantity models for the US, creating water quality profiles for vertical agriculture, and recirculating aquaculture systems, designing and developing real-time water quality sensors, and improving biofilm anode interactions for bioelectrochemical systems. So thanks for joining us. And then on the far end, we have Chris Reddy, who is a senior scientist at the Woods Hole Oceanographic Institution. And Chris studies how nature responds to uninvited guests to the environment, from oil spills, plastics, soot, or pesticides. He's committed to communicating how science works to the lay public, media, and policymakers. And Chris has published an estimated 200 peer-reviewed articles and book chapters and provided oral testimony to the US Congress 5 times and holds 8 US patents. So thank you all for joining us today. So like the other panels, we're going to start with a quick introduction from each of our panelists. Then I have some broad questions to ask you folks, and then we'll open it up to the audience and the panel members themselves for some free-form discussion. So I think we're starting with Michel. So that'll change the slide for you. That's the right-hand button. I think it's that one.
Perfect.
Yes.
Thank you very much, everyone, for inviting me here. I'm sort of a fish out of the water, as they say. I'm not an academic. I'm not a scientific person. I have an automotive engineering background, so anybody wants a custom car, come see me, but the rest of it, I know nothing on that. I'm going to start off with what we've done with Oceans United, and I have a small video that talks about a nonprofit that we started on a global basis to go after ocean plastic, pick it up, and try to recycle it.
Let me try again.
No.
Is that it?
No, that's the slides.
Oh,
You can start with the video.
Okay, 1 second. Here it is. No.
It's cool.
Okay, and no sound, right?
Yeah, there's no sound. Apparently is. It's just noise. So Oceans United, what we did is we started a small nonprofit org. The purpose was to find solutions to clean up what's in the ocean. It's not going to be the best invention in the world. It's not going to be the do-all to save the planet. It's just a technology that's out there now that we can use to try to pick up whatever mess is out there that we've created. And to be able to pick this up in the oceans, we had to look at a method of how do we get out there, how do we pick it up. There's a lot of groups out there collecting the plastics, a lot of groups doing beach cleanups, and all that is needed. The problem is what do you do with the plastic after you pick it all up? Now, does it get containerized and shipped off elsewhere to a sorting center? Does it get buried because you can't use the material, it's contaminated? So we, in turn, went and developed this ship in conjunction with a firm by the name of ICAT out of Australia. It's a 90-meter catamaran. It's about 27 meters wide. It's completely self-contained. So we can pick up the material, we can actually process it on board, generate the diesel fuel that we need to operate the vessel, and still have plenty of fuel left over to sell or to offer to disaster zones, beach cleanup groups, and so forth. Sort of our claim to fame, if you wish, is the technology that we developed. We took an existing technology called hydrothermal liquefaction, and we refined it to make a hybrid that allows us to take all forms of plastic, styrenes, nylons, polypros, and rubbers. We can take some biodegradable materials. We can take organic material and wood chips, process all that, and develop a diesel to sulfur-free fuel with this technology. We've implemented the technology, and we've just sold an additional 12 units that are going to be installed by Q1 of next year. Systems are running great so far. But as I say, it's just a current technology. There's a lot of other inventions out there that need to be funded or need additional research to take it to the next level. And that's what we're trying to do, is offer a platform that people can bring their technology. Let's get it out there, let's get it working, and let's see what we can do. Another basis of this technology was we wanted to develop it for land-based as well. So the exact same unit can be plopped down on a lot anywhere in the world. It's only 20 meters by 20 meters. It's about $6 million cost for the technology per se. And as I say, you're up and running in under 3 weeks at 100% capacity. So that's a little bit about what we did and what we designed. In relationship to today's program, I'll just let it finish. I talk faster than the video. All this technology was developed in Canada and in the US. We had a multitude of hours and months of research done by Southwest Research in Austin, Texas, as well as National Research Council in Canada. We have approximately 5 full-time scientists on staff working specifically on this technology. And we do all our own fuel filtration. We do all our fuel sampling ourselves on board. We have a new film crew that's going out now to get live images of everything. That's all set up. So.
Back to slides.
Yep, that's it. This is my first time doing this type of event, if you wish. So I really didn't understand what we were supposed to do. So what I did was answer the questions in my slides.
Good.
Perfect. So one of the questions that everyone was asking as well is, what is the length of time that these materials last in the oceans and so forth? And there's a lot of numbers that are out there. And one of the points that is coming across very strong in our meetings today is that there's no real standard and there's no real hard data as to when or how long it takes these materials to degrade or decompose at different stages. And one of the things I think would be very helpful is if we can get the petrochemical companies to put some sort of signature into the raw materials that they produce, so we in turn can identify it and maybe identify when this product was made and look at the different levels of deterioration. But that's a long-term wish list, if you wish, on it. But if you take a look at the materials, we consider, cigarette butts right down the fishing line as disposable. If you look at the years, fishing equipment, 600 years before it degrades. I don't believe it's that long at all. I think it's much shorter than we assume. We just don't have the true data to be able to say. Because when it is in the ocean, there's a lot of other effects that happen. You know, the wave action, the salt water, the sun on the materials and so forth. So I believe it degrades a little bit faster than that. Here's just another slide to give it a little more of a breakdown into the different materials. Glass bottles are undetermined. If it was unbroken, if it's not sort of washed against the shore and banging on the rocks, how long would it take? Nobody really knows on it. But styrofoam socks to microfibers from wool socks or what we call fast fashion nowadays, that's becoming a major problem in the oceans. And we really don't have enough data, and we need standardized tests, and I think earlier one of the gentlemen was talking about standardized definitions as well too. And I think there's more that has to be done. Is biodegradable also environmentally friendly? We don't know. You know, when this material breaks down, what's left? What's getting saturated into the ground? Everybody knows about the garbage patches, but you know, as we break it down, you've got your megaplastics that represent about 53% of the material that's out there. You've got your macroplastics that represent about 26%. You've got your mesoplastic that's 13%, and you've got your microplastics that's 8%. I think we need to divide this into maybe 2 or 3 or maybe even 4 more additional classifications for the material. Because there's material that's a lot smaller. As they were saying, you know, microplastics, people are considering it around 3 micron, I believe. And there's material that's much smaller than that. One of the biggest aspects of the garbage patches out there, 46% of the material that's in these garbage patches is fishing equipment, ghost nets and materials that are left behind. That's a large representation of material that has to be taken care of. And in the recycling world, everybody's looking for the same materials, the same components. And fishing nets are not one of them, right? So the sizes of plastic debris in the oceans, again, I think should be a lot of debate into what the real sizes are from the recent studies. This has been a generalization that's been used for quite a period of time. Which plastic floats and which plastic sinks on it. So again, plastic doesn't all float and plastic doesn't all sink, but eventually it sets into one of the substrates. And again, if you're looking at some of the tidal formations that are out there and the patterns in the oceans, some of the stuff will perpetually stay out there for a period of time. So that's going to be taken in consideration when looking at developing of plastics. Do you want something that can float and be retrieved afterwards? Do you want something that's biodegradable, that doesn't sink to the bottom, that can sort of go into a dust and go away? Wishful thinking again. Second question that we were asked was how are plastics transported into our waterways and oceans? And I think a great majority of us understand that it's fed into the oceans, let's say from primarily, I believe it's 10 river systems in the world that are the primary culprits to adding the material into the oceans. But because of the currents, they have generated what we call the gyres. And there's 5 main gyres that this material tends to circulate around. Some of the reasons, people that are much smarter than me in this room that can tell us exactly why they tend to migrate into these areas. One of the systems that we were looking at with Portsmouth University was looking at the current temperatures and how it kept the plastic suspended in the water in the upper levels before allowing it to go down to the lower levels. Question 3 that was asked was what were the energy and water costs for manufacturing of plastic and recycling plastics? Manufacturing of plastics, I don't know. I'm not a scientist. I'm not in the petrochemical industry, so I'll let the ones that do know answer that question. But for our process with our technology, what we're able to do is our whole system operates on a 50 kilowatt power unit at 3.75 gallons an hour if it was running at 100%. Our system, if we're running at 100%, only takes 35 kilowatts of power. That's 2.5 gallons an hour or 60 gallons a day to process 50 tons of mixed plastic, contaminated plastic. Out of that, we would produce 11,967 gallons a day of diesel fuel. Take out the 60 gallons that we need to operate ourselves, we're down to 11,900 gallons. When it comes down to water consumption, we operate our system at 80% humidity, and there's no need to wash or dry the feedstock that you need in a lot of other recycling processes. So our unit water consumption, based on 50 tons a day, is down to 2.5 gallons an hour, or 60 gallons a day on that. If we do a system flush washout, we do it twice a year. So we basically pressurize the whole system, clean it all out. It takes 800 gallons of water to do each time. That's a lot of water. So we retain that water, and we use that as our 60 gallons a day for 23 days after the washouts. So we're not taking fresh water to operate our system. We can use our recycled water. So the system at full capacity, 50 tons a day, the operational cost is about 68 cents for a gallon of diesel fuel when we don't have to pay for the feedstock. Up to $1.24 a gallon if we have to pay for feedstock. Majority of the target areas that we're going after, we don't have to pay for feedstock. So that'll keep us down to the minimal of 68 cents a US gallon. And if it's installed in an oil producing country, the system is still extremely competitive with areas like Nigeria, Kenya, Saudi Arabia, and so forth. And that's it for me. Sorry I couldn't address more of the issues of the environment.
Thank you. Next up, Glenn.
I'm going to be over here. So Glenn has an interactive. Is that okay?
Yep.
Perfect.
So, as mentioned, I work along with a number of people, John Marshall, who's over there, on trying to model the way plastic moves around in the ocean. And there are a number of problems with that. There are a lot of things that we know. We know how water moves roughly. We know how salt moves. We know that our models have errors, but they're not too bad. But then when you come to trying to understand plastic, there are a number of different problems because it doesn't necessarily move the same way the water moves. As we've seen, it might sink, it might float. If the plastic is floating and the water comes together, the water goes down, the plastic doesn't. That's why you end up with garbage patches. You've concentrated material. We don't know a lot about how plastic gets into the ocean. We do know that a lot of it ends up on beaches, and that says that the surf zone is very important. What's happening right near the shore is obviously taking material that might have come down the rivers and ending up on the beaches. Next big storm, it may end up back in the ocean. We don't know how big the source is. What we do know is this is a good area at least to clean up. You can see it, you can clean it up. The other source, much of that source is coming out of rivers. So this is an example just showing the production of the rivers, with the big circles being 20,000 tons a year coming out. You can see that there are a number of major rivers. You can also see that in the United States, which we spent a lot of time on this morning, we've done a reasonable job at trying to stop that. But what this says is that this is not, the solutions that work here, we also need to think about solutions that will work in many other countries, and in some cases, many poor countries. The other major source, as mentioned, is fishing gear. This is just a record from cross-Atlantic transects, where they're doing plankton tows, but they recorded when their machine got all gunked up by plastic. Most of this would be large stuff that basically stopped the processing of the machine trying to measure phytoplankton or zooplankton. And you can see it starts in the 1950s. The first one was 1956 or 9, where they first found a piece of ocean plastic. And then there was a big rise, and then it's kind of tapered off for them in this area. But much of this is large plastic and probably is related to fishing activity. Okay. So when you try and model it, what I've done is sort of written in black, things that we know pretty well, and written in red, things that we really need to know a lot better in order to try and understand the distribution. Where is this stuff liable to be? Okay, so we know about all kinds of processes that act in the nearshore region, the rivers and the beaches and the estuaries and the coastal waters, all of these things, tides, currents, longshore flows. We can get a reasonable insight into those, but in order to apply them to plastic, we have to know what is the real source, where is this stuff actually entering into the water, and we need to know, is it just floating? Is it sinking? Is it going to end up on the bottom of the ocean right near the shore, or is it going to go offshore? And we don't know very much about exactly how different types of plastic at different sizes and different shapes will sink or float. We don't know a lot about what are the real mechanisms that take it from the shore area in the surf zone and the edges of the rivers out into the deeper ocean, and how it gets into the coastal ocean, and then from the coastal ocean, how it gets out. In the coast, one of the major processes that we know about is that when the wind blows along the coast, there can bring water up. If water's brought up, it goes out in the surface and it carries the stuff with it if it's floating on the plastic. So that's one of the mechanisms by which we can get material out. But there are also problems in understanding the coast. At the edge of the nearshore region where the ocean bottom drops off, called the shelf break, there often is a current there, a front, and that may block material going through. So you may end up kind of trapping a lot of it in the nearshore region. But there are also small motions, we call them eddies, scales on the order of kilometers to 50 or so kilometers in size. These act like turbulent stirrers. So they can mix the stuff out, mix it across, and get it into the deep ocean. And again, there's the issue of settling. So as mentioned, we don't know very much about the distribution, but this is one bit of data. This is from the deep ocean. It was taken by WHOI et al. With an instrument that was lower down into the ocean in the upper 1,000 meters. And what you see is what they measured as plastic, and it clearly is not all at the surface. There's a large amount underneath. And so if we want to know where is the plastic in the ocean, again, this is one bit of data. It may not be representative, it may be representative, but it's certainly indication of a problem. We don't really know how much is subsurface in there. If this were true, it would say actually the majority is subsurface, which means we can forget about trying to clean up the ocean. And we concentrate our efforts on the nearshore areas and the rivers and trying to both stop it being produced in such a way and being put into the rivers and ending up in the ocean. Okay. So once you get out into the ocean, then there's a question of why does it accumulate in particular areas? Why are there garbage patches? As just mentioned, there are these 5 areas, and one way to look at those is if you think about something trying to accumulate, you need to be sitting at a point where the average velocity is pretty much 0, right? If it weren't 0, it would end up moving someplace else. And so if you look at output from a model and ask where are the velocities 0, the 2 lines are the 2 different velocities, the east-west and the north-south, and the places where they cross are possible accumulation points in there. And so you can see an accumulation point in the Pacific over about in this area, and that's right where the Pacific garbage patch is. You can see the one in the South Pacific. So these are possible points where the material might accumulate. It will only accumulate there, again, if it's on the surface, it will only accumulate there if you have this kind of inflow and downflow of the water. So the plastic comes in, goes down. The water goes down, but the plastic doesn't. Okay. However, if it's in there, but it is also in a region, as most of the ocean is, where you have these strong time-dependent stirring motions, then it doesn't just sit there because it's going to be spread around the same way if you put a drop of milk in a very still coffee cup, it will sit there, but as soon as you start to stir it, it spreads out. And simulations of that kind of process, these were done by a grad student in the joint program, show this kind of spreading. So these are simulations over hundreds of years, releasing particles all around all of the coast. And that's not necessarily what happens, but it gives you an idea of how it spreads out and how you end up with these patches which are large scale. And so in the Pacific, you have regions covering millions of square kilometers, and this stuff is just spread out over that whole area. So understanding this kind of thing gives us some idea of where the material is and where it's liable to end up staying. But again, in order to be more quantitative, to be more sure about that, there are the issues that we don't know very much about. How does the material sink or float? How does it break up? Because once you break the pieces of plastic up, that changes their characteristics, their sinking or floating. And how does it degrade? If you change the composition, if you break it down into something else, as just mentioned, is that something else good or bad? If you break it all the way down into carbon, well, that's probably not too bad. But if you don't, you may end up with other materials which are just equally toxic. The plastics are harmful because they are such long, big molecules that most bacteria and things have trouble with them. And so it's not clear what the degradation process actually is, how fast it acts, how do you put it into a model if you don't know what it is. So these are the kinds of challenges, the things that those of us who are interested in trying to make models to understand the process, and for people who are working in coastal areas trying to make models that you might actually be able to use to help in nearshore cleanup. All of these come up against these issues that we need better data on. We need laboratory information on how stuff sinks in seawater. We need to understand how the bioaccumulation on the plastics changes the density, causes sinking. There's room for a lot of interesting research. So I will leave it at that.
Perfect, thank you. I think Chris is next in the slide deck.
Okay.
You
want
can use the clicker if you like.
Oh, where is it? Oh, okay.
Yep.
Thank you. Thank you for having me here today. Yeah, that's actually really nice. We get to see our screen right there. I started thinking about plastics maybe about 10 or 12 years ago, and I had to take a little break from it because I studied it. I had another research interest that I followed down, and then I just came back into plastics a couple years ago. So it's been really interesting for me to see how the field, I literally was out of the field for 10 years and then got back into it. So it's been very interesting to see how the field has changed in that 10 years. I want to start off with a quote by Edward Deming, who was a statistician, business person, economist, an incredibly brilliant person. And he said, "In God we trust, and all others must bring data." And I say that, and I'm going to go one step further on Deming and say, in God we trust, all others must bring environmentally relevant and life science relevant data. I say that in the terms of plastics because in the 2 hours since I've been here, I probably heard 10 or 15 catchphrases or statements that I've looked into. Many of them are not peer-reviewed. None of them are not very well defined. And furthermore, there's a lack of uncertainty. And I think Glenn did a fantastic job explaining uncertainty. I would go one step further, and if you looked at that WHOI figure, the downwater water column profile that Glenn showed to give you some insight about whether or not if there was sinking, that there would be a significant mass in the subsurface. I looked at that figure and immediately said, and I'm not knocking Glenn, I'm actually asking the scientist who wrote that figure, what are the error bars on those data points? What is the uncertainty of the measurement? No, what is the uncertainty of the collection? What is the uncertainty of the measurement? Where is the quality control? Because you could easily argue, when I look at that data, of 2 to 8 particles per cubic meter, 1,000 liters, that all those numbers could be the same. So I guess what I'm trying to start off with is that wherever you're coming from, now I'm a scientist at heart, wherever you're coming from whether you're policy-driven or an activist or trying to look at this from a business opportunity, we have to ask, where is the data? Where is it sourced from? And whether or not it's robust and meets the bar. If we don't do that, as much as it might feel good or taste good or think good or whatever, we are making a critical mistake. I am not saying that plastics are good. We do not want to get in the luxury of the future of, and this is not just plastics, this is a global concept, of not having strong data before we make policy-driven decisions that's coming from science. Often, policy-driven decisions may have environmental issues at heart, and within them, but they get overruled by other factors. We don't want science being communicated without any peer review or any types of substance. That is what we see a lot today. Challenge people when they make a statement. I know it's hard. I'm up here giving you some halitosis. So, I'm breathing fire probably and aggravating some of you folks. But ultimately, we will all be better off, and we will have a much more successful outcome of reducing plastics and other stressors to the environment if we raise the bar. Good scientists are better skeptics. And we should all try to be a little bit more skeptical about what we hear so that we can make the most well-informed decisions and limit any more harm that we do to the environment. So I show this figure. This is some of my research interests. When you look at them, you might say, well, he's particularly fickle in what he likes to do. And that's true. It's kind of fun to think about other stuff. But when I look at that figure of whether I look at soot or what happens to building roads with recycled automobile tires, all 6 of these examples and others represent carbon. These topics are all organic carbon. We have had a long history of studying the carbon cycle and the fate, source, and transport of both natural and human-made types of organic carbon. I think we're missing an opportunity to spend a day in the library instead of a month in the lab. And there's a great chance for us to enrich ourselves and take advantages of what other science has been done and other types of carbon-derived pollutants and look at what we've learned from that, learn from those lessons, and then move forward. One example is soot. Soot is the incomplete combustion of organic matter. Well, it's very interesting because there is no one, you can buy DDT as a standard and do a very nice job analyzing it in blood or blubber or wherever. You can't buy soot and think it represents one single entity. It represents a spectrum of a continuum. And it also depends on whether it came from burning wood, whether it was oxygen deprived. These types of complexities that scientists have faced for many, many years of studying soot could easily be transferred into studying plastics. And how soot, and what they call black carbon scientists and health scientists pivoted, recognized the challenges that they faced due to the uncertainties and the vast types of soot that out there, and decided this was how they were going to develop their research programs. So I really want to underscore the opportunity that, first, plastic is carbon. It happens to be rather interesting because it's only been produced, let's just say, from 1950. We have a good idea that it's coming from land originally. It's extremely tough in a relative scale. And And it also has what I would consider a radiocarbon dead. It has no amount of, most of it's fossil sourced. So it gives you actually a really opportunity to study it. And it's a wide-ranging, open opportunity. So with that said, and I've been thinking about pollutants and studying organic compounds for about 25 years, I would say without any doubt that the hardest project that I will ever be involved in is studying the source, transport, and fate of plastics. It is an extremely non-trivial effort. Does it mean we shouldn't do it? No. Actually, I think it has great opportunities. I think it's fantastic to do it. It is a non-trivial task. It will take decades for us to be able to have the certainty that we know about other pollutants that exist in the environment. And I'm going to try to talk about two MIT professors. One was a guy named Ron Heitz, who's now at Indiana. He might be retired. And Ron, maybe in the early 70s, late 60s, wrote one of the classic papers about polycyclic aromatic hydrocarbons, or PAHs, right there in the river. Stone's throw away. Raised the flag in terms of that problem, what they exist. To this day, we have still not really hammered out the biological and toxicological impacts from PAHs. I mean, we have a really good understanding, but there's still gaps because science is incremental. It's ever expanding and it's self-correcting. So we can do this, but we have to understand that science takes time, and that's okay. I'd rather be patient than off. Some of this is my takeaway, and some of this is a little bit of a hypothesis. I have a hypothesis that should be easily, well, not easily testable, but pretty straightforward. I argue that plastics are not one of the top 3 or 4, at least, stressors to the ocean. I do not think, when I hear people say that plastics are going to kill the ocean, is true. It's a testable hypothesis. Maybe not now, but soon. I would like to see that. I think that these are the types of questions we should ask as scientists. I think but how many problems that we hear about today can be solved? We can't put rolaids in the ocean to solve ocean acidification. It's not that easy. It's extremely complex. But we can reduce the amount of plastics that's going into the ocean by a lot of the stuff that we've talked about, I've heard you talk about today. So there is great hope. There is a victory to be had, that we can show that we can make a difference. It's a great opportunity to learn about nature. It's also a great opportunity to encourage and recruit the next generation of scientists. So I think it's a great place to start. I think studying plastics is something, again, that we can make a difference on a timescales that are relatively short. I think some of the stuff that's been going on and whether or not it's really well-defined policy or different habits or different manufacturing or different cleanup techniques and technologies, we're going to see results relatively quickly. That's pretty impressive. I mean, it's not to say it's all going to go away, but I do think we have to celebrate that. I do think that plastics has a little bit of an Instagram effect. It's pushed up a lot. I tend to think of it as it has kind of like a media inflation. And I always try to tell people that if carbon dioxide was black, I think our awareness to the increases of carbon dioxide in the atmosphere and its potential changes to climate change would be so dramatic that we would ever have any talks on plastics. It would be so alarming to us to see that pictures of our parents' wedding had a very clear background, and now my wedding picture with my wife is gray. Although I'm really happy. The background, run with me there, I'll stop. The point of the matter is the interesting thing about carbon dioxide is that the science of carbon dioxide, resting upon the Keeling curve and other opportunities, the uncertainty, well, let me put it this way, let's be positive. The certainty about how much carbon dioxide is in the atmosphere for CO2 around this world is extremely tight. Keeling laid out a beautiful vision to start collecting CO2 data in the 50s in Hawaii, and which has grown across on a more global network. That is what we need to aspire to. We need to, and Keeling was so wise about recognizing the need for high levels of quality control, which has been spoken about today. I don't think we'll ever get to a Keeling-esque CO2 curve in part because CO2 is an individual molecule that can be measured a variety of different ways. But let's aspire to generating data and minimalizing the uncertainty. And also recognizing that just because we don't see it, it isn't a problem. Again, I'm not minimalizing the plastics at hand, but recognizing this whole concept of uncertainty. My wife sometimes says I can come off as a jerk. Probably doing a good job today. I have a really happy marriage, but it's true, she says that. I think scientists have to be ready to tell everybody to raise the bar. I think it's high time for us to say, no, that's not good enough. And I have this extreme desire, and I'm going to leave it at this, that one of the first papers on plastics was written by Carpenter. He was a scientist on it with Oceanography. It came out in, I think, Science in 1970 or 71. If you go back and read that paper, it's really, really well done. In fact, I am tempted, and I've been trying to contact at least 2 editors, kind of tongue-in-cheek, I wouldn't do this, that paper is so good that if you put in a couple recent references and you just tweak a couple words so that it sounded like the work was done in 2017, you could publish that paper face value. What does that tell us about the state of science and plastics if the paper that was written in 1970 could get published today? In some respects, it's okay, but my point is that we need to start pushing harder, asking scientists, where'd you get the data? How tight is that data? What are the uncertainties? It would be perfectly fine with me if I heard somebody say the amount of plastic that we eat is the size of a credit card plus or minus the size of your house, right? We hear the size of the credit card, which may be not a bad number, but it's based on a lot of uncertainties. Uncertainties can explode. Demand robust science, ask about uncertainty, and I think we can even make a bigger difference than what's already going to happen in the fate of plastics in the environment. Thank you.
This quick. Hi, good afternoon. My name is Dave Sanchez, and I'm going to spend the rest of the time telling you how excited I am to be here. Right. So I'm from I live in Pittsburgh. I'm at the University of Pittsburgh, and I'm an assistant professor in environmental engineering. I put up this picture because Pittsburgh has a lot to do with legacy, especially when it comes to environmental issues. If you think about acid mine drainage, if you think about the steel industry, if you think about coal, if you think about what Seth mentioned this morning, right? Rachel Carson and DDT. In Western Pennsylvania, there are a couple other connections here to water and plastics, that's pretty important as well, right? So I think John alluded to Sherry Sam Mason, whose research helped lead the ban for microbeads in the Great Lakes, right? There's another connection to Pittsburgh, and it's that your MIT Water Summit director actually did his undergrad over at the University of Pittsburgh. When I was asked to be here, there's one thing that stuck in my mind when it said MIT Water Summit, drowning in plastic. And the thing that came to me was the fact that it seems that putting water in a plastic bottle is just as easy as putting plastic in the water. When you look at everything going around, right? It seems that putting water in a plastic bottle is just as easy as putting plastic in water, and that's with a bunch of the things that are shared here. My goal is probably not to talk so much about what's being the fate and transport within the water, but maybe an approach on the design side and share some of the things that we think about. So I'm head of Sustainable Design Labs. These are obviously the people who do all the work. And we'll get to it. When this panel is all about the life cycle of plastic, and what I want you to see here, right? The first thing I want you to see is that there's no arrow pointing to waste, right? And the reason why is because given what we have for plastics, right? This is the idea of what the life cycle for recycling plastics is. Understand, I'm with you when I say yes, there needs to be a paradigm shift, but are there design opportunities to create this paradigm shift? Right? Are there design opportunities to go ahead and insert in here some clever design where you're working with an anthropologist to go ahead and intuitively let this degrade right after it's used? right? In our center, there was Eric Beckman received Ellen MacArthur Foundation grant to make the unrecyclable plastics more recyclable by working with polymers. He's a green chemist. To give you a couple of numbers, right, because this is about life cycle and life cycle impact, it was Peter Gleich and H.S. Cooley in environmental research letters that talked about, they projected what the energy and the energy impact for plastic water bottles was. And so they didn't say, hey, it was primarily secondary data. But the idea was conceptually they were able to capture what the embedded energy was, right? And so, well, where does that energy come from? So if you look at this cycle, obviously in the feedstock, there's raw material extraction. And then when it comes to plastic production on the top left, that's dealing with creating your resins, creating those little pellets, right? And then you do the product manufacturing. And if we're just thinking about the plastic water bottle here, that's actually the blow molding that happens. So when they actually blow up your plastic water bottle, takes its shape. And then you get to the use. And then finally, we're mostly talking here about single use. After that single use, there's mechanical recycling where most of it gets chopped up and it gets reused. What they projected, and this is what they did, they said, imagine there's a water bottle that's coming from a local place, and one coming from France, and one coming from an island in the South Pacific. I think they were referring to Fiji water. I'm not too sure. They didn't cite that, right? But what they talked about was, a lot of the energy, happens in the production of the plastic. And so they said, okay, raw material extraction, plastic production, filling the water bottle, sealing and capping the water bottle, then transportation, and finally cooling. And so they said, okay, it's about 5 to 10 megajoules, right, per liter of water. That's what it was. And so if you're trying to think about, well, how does that relate to some of our other energy uses? In a house, we're just going to go with, maybe an average house, you're using 200 kilowatt hours a week, okay? If you're using 200 kilowatt hours a week, right, that in plastic bottles is just 150 plastic water bottles, based on 5 megajoules, right? If it's 5 megajoules to make each plastic water bottle, so 150, don't try to go home and power your house with 150 plastic water bottles, but the idea is that's the equivalent, right, of the energy that's embedded into your plastic water use, or plastic water bottle. With the water, it's a little harder. You get all sorts of ranges. What's funny though is even the international body for plastics, right, for plastic bottles, they even estimated it was over, they estimated 1.4 liters of water is used to make the 1 liter of water in your water bottle. So their estimate is even over. Others, depending on how you're accounting for this virtual water, this gets into life cycle assessment and environmental impacts. They're talking 3 to 6 liters of water per liter of bottled water. And so these are kind of some of the embedded impacts when you're looking really just at our biggest single-use plastic, which I would say is probably plastic water bottles. I'm going to hop over just here real quick. I'm going to break down the design challenges, I think, really boil down to kind of like these 3 things. Right? One is recycling. We should probably get this out here. Recycling isn't really about the planet. Recycling, as it's done, is normally done based on profit. So if you've lived in a county, sometimes, maybe you have this experience, maybe you don't. You go out, and then all of a sudden you get something in the mail that says, hey, we're no longer recycling glass. And then they say, oh, we're no longer recycling number 5, or something like that. Well, you're wondering, like, what happened, right? Did you switch CEOs? Did you switch missions? No, often it was with the recycling market. So that drives it. So cost is a very big thing when you're talking about, well, how do you actually design things to go ahead and beat that cost curve so that you can actually enable it to be recycled? Other one, all of them are C's, so they should be pretty easy. Consolidation, right? So consolidation is the idea of bringing all the plastic together. You saw that people were talking about different leakage rates. People were talking about different places where the plastic ends up. Right? One of the things that's really hard, and you see this, and what I'm wondering is why don't designers hang out with anthropologists and look at how people use plastic water bottles, right? How about the idea is that for every product that you have, intuitively you would know where it goes and what it does based on how it's designed. And what's the analogy here? Everybody knows when you walk out that door, you're going to push on the gray silver bar. And you know that, it's quite intuitive. There's not really instructions. There's nobody in a mechanical voice, like at Boston Logan Airport, saying, step here, stand here, or walk here. It's quite intuitive, right? You can build some of that intuition using how people interact with their products, right? Form follows function. And so if you want the function to be able to be recycled easy, embedding that into your design, it's probably pretty important. So cost, consolidation. The next one I would say, as I'd point to the top up here, is complexity, right? The multiple colors. So if you think about it, is all PET is not the same. And the reason why all PET is not the same is because sometimes that PET is embedded with a different color, different additives, depending on what function you want. If you want it to be, temperature resistant, maybe you're adding a little bit more, a few more additives. If you're actually designing it to be more structurally sound, maybe you're creating multiple layers. And so when you're doing this, the complexity of this, trying to go on and sort that out is why only 9% of the plastic is recycled or projected to be recycled. It's the complexity of what we have here. But imagine, again, a design opportunity where you're, how do I design things? How do I simplify what, our materials so that we can actually re-assimilate them? Right? One of the most shocking things to me when I was starting to engage more with biomimicry is that they were talking about the peacock and its feathers and its colors were really based on 6 structures. Right? I can't dive into it. When I was told that, I was like, wow, can't we actually produce some of the same complexity, maybe using a different approach to design, right? That less is more in this regard in terms of using more simple materials, and that allow you to re-assimilate plastics. So what was that? Cost, consolidation, complexity. Final one, contamination, right? So everybody should know here, right, you don't really take your pizza box and throw it in the recycling bin because of the food contamination. How about the little bit of orange juice that you just left, right? What about the rest of your bagel or these other things or your ketchup, right? So that contamination is one of the reasons why things also get disposed of and not necessarily recycled. So these are very, very big challenges when you're looking at the overall life cycle or the impact of these plastics. But there are design opportunities. So if you think about what mimetic approach is, think about benign by design, where people look at toxicology and they try to reduce, using green chemistry principles, the effect that your materials have on others. So I see that there's lots of opportunity here. I'm going to get to a couple final things. One is, it was mentioned earlier today talking about, how many drinking water treatment plants there are. Well, with EPA, right, there's 156,000 drinking water treatment plants. Right, in the country. And you're like, well, where are they at? Well, actually, the majority of the country is served by just 5% of those 156,000. Wow. Okay? Everything else serves 10,000 people or less. And so when you think about, how is the public exposed to these things, especially when it comes to water, when you're comparing water in plastic bottles versus water that you get from the tap or things like that, I bring up this thing right here. And I know it says wastewater treatment plants, but you can imagine wherever there's wastewater, there's probably water somewhere nearby. There's probably a groundwater well, for sure, in many of them, but there's also probably many of these small utilities. EPA has a specific focus on small systems because there's a large amount of our population that's exposed to contaminants, maybe things like microplastics, or the contaminants that are carried on microplastics through drinking water. So it's a very, very big important thing. The other reason why I bring up wastewater treatment plants is, Glenn had mentioned that in the US, relative to some of the other places, when it comes to plastics, making its way through the rivers, that we're doing relatively better. And it might be because Karen and Demi are doing such an awesome job, and so we get to remove all of them, right? The other part that I want to think about is wastewater treatment plants as places where you actually get some more of this, refuse or this trash. This is the water summit, and so you think about the life cycle of water. Plastics get flushed down, leave in wastewater treatment plants, but there's other issues, and I bring it back to legacy, right? In Pittsburgh, what you'll see is we have something called combined sewer overflow problem. What does this mean? Back in the day, your rainwater and everything you flush down the toilet went in the same pipe, right? It was quite efficient because the thing is everything went to the same water treatment plant. Now the wastewater treatment plant that we have in Pittsburgh can service 280 million gallons a day. That's a lot. But here's what happens when you have CSOs, at least in Pittsburgh, which is our legacy problem. When it rains 1/10 of an inch, right? The water treatment plant, wastewater treatment plant would be overwhelmed. And so some of it is directly discharged into the river. What does that include with it? That probably includes tires. We've been on the boat and seen that. Plastic, all the things that run off, all the things that are dripping from cars, all these other carriers of pollutants that go into there. And so that's the thing that happens with CSOs. So when you're looking at wastewater treatment plants, right, we're probably exposed to a lot of things, including plastics, through these systems. This is just a final thing to kind of show you. We, as part of work that we do, we go out, measure. That was the one sampling thing I took. Everybody else did everything else because they didn't want me to sample. And what we'll do is we'll measure certain parameters, right? The fact that I have total nitrogen and conductivity here is just looking at a pattern. The bigger thing is we're mapping some of these water quality parameters with other things, like BPA. Now, a couple of people mentioned, like Diana mentioned, BPA earlier today. And so for us, it's trying to track, in a way, using proxies, BPA and where it's coming from. Because even though it's coming from CSOs or coming from wastewater, there's a lot of non-point sources. There's a lot of things that are flowing, that are washing off. And the way we do that is we build real-time sensors to measure other parameters while we're taking grab samples. And when we do that, we take that data, we map it over the data what we got for the concentration of things like BPA, right? But what we're really doing that's really unique when we think about the life cycle is it's hard for me to find places that are trying to treat the contaminants that are leaching out of plastic right where they are in the environment. And so for us, we're pretty fortunate. We just got an NSF grant. We just got an NSF grant to go ahead and look at, we're using biofilm electrodes to kind of actually degrade bisphenol A right in the river. And the idea, here's the idea. Many of there's microorganisms that have genes that have been shown to degrade BPA. Can we actually connect to them using electrodes to go and accelerate that, that degradation, for BPA? That's what we're going to find out. The final thing as I think about, legacy and another Pittsburgh reference, the canary in the coal mine, is I think about, this place, right? This is my home. So this is where I was born and raised. And as you can see, it's surrounded by water, right? I took it for granted. The most gorgeous views ever, seeing water going, every which way on each of the beaches. We survive off a freshwater lens in there. And so many of the things that we're talking about here that motivate what I do are accelerated, on scales like this, right? Whether it's, anybody know where this is? No, you can't say anything. Yeah, this is the island of Guam, right? So this is over the Pacific Ocean. So we've done stuff there, went down to Jamaica, looking at comparisons. But here again, right, when you think about it, I know we're looking at very global matters. Sometimes they're very accelerated in places like islands. And yeah, that's my time. Thanks so much.
Great. Thanks so much to our panelists. So we've spread out pretty broadly, and you guys have touched on some of our discussion questions already. So I just want to bring us back together, and we'll go through these questions fairly quickly to make sure there's time for the audience to ask questions. But first, so the first question about what's the lifetime of plastic and what are the common ultimate fates? A lot of you guys touched on that. I wonder if you have additional things on misconceptions about where plastic actually ends up. What do you think people might misunderstand about that? And then the other thing that I didn't hear anybody mention, I think, was biodegradable plastics. Is the ultimate fate of those plastics different? And I'm going to let you guys, whoever.
Yeah, I'd love to comment on that with a comment and then a design challenge. One of the comments is, for bioplastics, there's always some sort of intuition you're giving to that term. So sometimes bioplastics, you're intuiting that it's probably going to be biodegradable. That's not necessarily always true. It just means that the precursor actually just came from corn or something like that. The other part, right, for not bioplastics, but the other part for food packaging, for example, the design challenge I have is, why wouldn't we design our package the way apples are made, right? With an apple, you don't use a package, right? The package is actually edible. And so there's some creative ways where people are going and making things where the package is edible, right? I mean, it's biomimetic, but it's kind of how nature does a lot of these things. And so, yeah, I don't know exactly all the fates, but I do know some things I'd like to see, perhaps. Yeah.
In Japan, what they did is they developed an algae that encompasses water. So instead of having a water bottle, it is a bubble that you put in your mouth, and you just consume everything. I don't know how you transport it, but it's a start.
In your pocket. Yeah.
Going back to whether it's bio-based plastic, which is a really good point, or whether it's biodegradable, there's a huge difference between taking a piece of bioplastic or biodegradable plastic and putting it into a flask that is chock full of nutrients, no other carbon source, and seeing whether or not it can biodegrade. And then also trying to get some type of time constant. That's entirely reasonable because it sheds light on whether or not the bugs have the skill set or the tools to want to biodegrade this or can biodegrade it. The rub is that for any product that we tend to think is biodegradable, and I'm not going to argue that it's biodegradable, but microbes are like teenagers assigned a chore. They only do a job when they want to do it, when it's convenient to them. And they, most often or not, if you assign them to clean the garage, will frustrate you because they don't complete the job. And that is the problem with microbes in many, many cases. We have grand expectations for them, but they often let us down. And it's not necessarily their fault. And I know there's work going on. Plastic itself is not very palatable. And so you have to ask yourself, in nature, when you want to design a plastic, you have to figure out a way that a microbe is going to choose to eat that over the other buffet of plastics that might be in the ocean, whether it's algal debris. So the challenge at heart is to recognize and build products that, if they're biodegradable, make them not only biodegradable, but get them high on the list of the buffet. So whether it's whatever thing that you would go to the buffet first, that's what you want. Don't make it not tasty, because the bug ain't gonna eat it.
Great.
I suppose my example of misconceptions is when I was looking for some nice pictures of the garbage patch, I found it labeled as a new continent in the Pacific. But I think it speaks a little bit to one of the issues that maybe is relevant to a broader question relevant to Chris's talk, and that is, we've been bedeviled in the climate by people who say, scientists aren't sure, so we don't do anything.
That's right. Yeah.
And that's what we want to avoid. We want to know better what's going on, but at the same time, we want to take what actions we can now that we can identify, because we know there's plastic there.
Absolutely.
It's very hard to think that it's good.
That's right.
So we should go ahead and move at the same time that we're trying to get a lot better
I agree.
data.
I agree.
Great. Wonderful. Do you have another one? Okay. Okay, so about transport in our waterways and in the ocean of plastics. We talked about the Pacific Garbage Patch, these guys that are collecting plastic. What are the other hot spots? Like, how significant are those? Like the Pacific Garbage Patch, I know in the previous panels people talked about hot spots maybe in estuaries or these other places that plastics might accumulate. Yeah, I'm wondering if folks can comment on that.
I think it's a massive global problem. It's not just 5 centers. It's not just 10 main estuaries that are feeding in the material. It all starts in, let's say, your municipality with your curbside collection. How much of that material is actually being recycled or being thrown into landfill? As they were talking about earlier, contamination of the materials. It gets discarded and it goes off and gets buried. If it gets buried, and it moves on from there. In the UK earlier, they were talking about waste and so forth. In the UK, they've tried to force people, when they are a recycling or an environmental company or whatever the case may be, that they pick up the material, that they just don't go and dump it in the ocean and keep the tipping fees in their pocket and so forth. So they're forcing them to put bonds. So putting more legislation in place, making the people that are picking it up or supposed to be recycling it more accountable for doing that, or for cleaning up the mess that they create for not doing that, and so forth, or going down to the point of putting deposits on the materials. In Quebec, I live in Montreal, so we've eliminated all of the plastic wrap that goes around meat and fish and so forth. You show up with your own container. So they have the meat preparation area or the fish preparation area. Then there's a space like a quarantine space where you can put your container, they put the product in there, and you walk away with your material. So there's no more packaging material. So it's changing of the habits and making parties responsible.
Yeah, I mean, I think part of the hotspot, I mean, this has been a global phenomenon because of the fact of, with China accepting, everything, they created, it was quite easy for us to offshore that plastic. Since they banned it in 2017 and enacted in January 2018, now the plastic is being offshored to other countries, Vietnam, Malaysia, but they'll soon close down. I mean, the reason why China generates, a lot of plastic and had a lot of the recycled waste, and so maybe that's the reason that 8 out of the 10 top rivers where most of the plastic comes from is there. But I think one of the things that I don't want to miss is the fact that there are still a lot of non-point sources here, and they're all byproducts of the same paradigm. It's the fact that we live in a culture of single use, right? And so, when it comes to policy, if you just look at the US versus Europe, Europe has set goals, right? And so their recycling rate is more to 30%, while ours is maybe 9%. And so they've set goals, they're trying to create incentives there. And that's the hot spot of, while most of the plastics over there, a lot of it originated from places like here.
One of the issues, as you were saying, with the shutdown of China or Malaysia or the Philippines or whatsoever for the acceptance of the raw material to come in there is they realized that, number one, they weren't just getting clean, recyclable materials. A lot of that was contaminated. It was part of a delegation that represented Canada to go over there and suck up to the Philippine government for our 169 containers of contaminated waste that we had to get out of there. And President Duarte's opinion was, look, you made it, you packaged it, you clean it up in your own backyard. So is it maybe a point in time where we have to start looking at a cradle to grave responsibility for the material? It's done in some other industries and segments. So maybe that's something that's got to be done where we have municipalities that start recycling the materials or taking responsibility for proper disposal of the materials in their own areas versus just let's get it out of our lot and move it on to somebody else's lot.
So I think one of the hotspots that I think about is, you go back to the Geyer paper in Science, which did an unbelievably fantastic job of looking at production of resins over time, and it was allowing them to do some mass balance calculations. And I think it's one of the must-read papers that if you want to have a feeling for what goes on in plastics in the environment. I had this Brazilian scientist visiting me for about a year, and they were analyzing some sediments downstream from where he lived. And I said, what are all these compounds? I've never seen them before. And I said, what's around here? And he said, oh, these are all, I'm not going to get the translation right, but these were all plastic companies that were off the books. These were companies that had no, they were basically operating under the books or, or illegal. I'm not quite sure how you would phrase it, but the point of the matter is, the question I keep thinking about is, are we actually making even more plastic? Are we even making more plastic because it's slipping through the cracks because we have a lot of folks who are producing that and it's not getting caught in these fantastic Excel spreadsheets that Geyer made, et al. And I think even one step further is that the one thing that I don't think we think about that often is that downstream from that plant, the sediment was extremely contaminated with some organic compounds that we were able to figure out what they were. But they weren't in what we would call the typical target analyte list, which means that unless you knew what you were looking for, you would miss them. And at the end of the day, these sediments were by far the most contaminated by the raw materials that did not get properly synthesized. It really startled me that the plastic problem could even be much larger when we started to think about the incomplete products that you get in the waste stream, as well as the ones that aren't on the books already. Great.
So our last sort of broad question, the original question was, what are the energy and water costs of manufacturing and recycling plastics? Or sort of more broadly, what are the difficulties in reclaiming plastics? And I know David touched on some difficulties, but what are the barriers to recycling plastics?
Yeah, I think the only thing I'd add to that is, I talked about costs, complexity, contamination, consolidation. I think those are all a lot of challenges. But the other part to see is, there's a lot of engineering to making it easy enough, just as easy to put water in plastic as to put plastic in water. And so like whether it's Nestle or Coca-Cola, like they've done a lot to already make their bottles lightweight. Right? So there's a lot of engineering to reduce that cost, really because for them it's it's economical, it's beneficial, right, to find some innovation in that regard. And so when it comes to those costs, the numbers I shared are there, but for them, I'm pretty sure they're always pushing that number to make it to make it better, whether it's the 5 megajoules per liter of water, or whether it's the equivalent of 1.5 liters per liter plus. I think those are baselines. I don't think those are going to shift as much. I think the bigger thing is how do you design other things, other functionalities into it, moving beyond energy and water costs. Yeah.
Great. Does anybody else have a comment on that?
I think there's a big kind of social barrier to plastic recycling because of the necessity of cleaning it.
Yeah.
And people just don't do that. You don't take your plastic plate into the sink and wash it all off carefully before recycling it. And so we need recycling methods which basically can deal with that kind of material.
Yeah, the post-consumer contamination of plastic material is just absolutely enormous, and all that is going to landfill. Nobody wants to take that. So developing technologies that can actually take those materials, take all the styrenes and the rubbers and the polypros and so forth that nobody really wants. There's a lot of material out there that's got to be recycled, and it's the technology to be able to do that. And I mean, we stumbled upon one. We didn't go out with a mission of trying to find it. We stumbled upon it. But it's far from being perfect. I mean, there's a lot more work that needs to be done in what are we going to do with it? I mean, a lot of people using technologies like gaseous pyrolysis or pyrolysis systems or other hydrothermal liquefaction systems. What are they doing? They're making the base compound to make more plastic. We don't want more plastic. There's enough of this stuff out there. Let's try to take this material and create it into something else. We're making diesel fuel. That's not ideal. We're putting more carbon back in the air by burning the stuff. But what can we do with this material? What can be developed, or what technology can be brought forth that we can take this and make it into something that's good for the environment as a whole? And that's where we need MIT to step up.
Well, one thing I would add is like it could be, there are situations where it costs more, it's more energy intensive and water intensive to recycle than it is to generate something new, which is probably enabling the current paradigm. Yeah. Right? So if I have to wash, clean, sterilize, I mean, the process of reclaiming certain plastics is also energy intensive. And if that beats out the 5 to 10 megajoules per liter, but then for them it makes no sense.
And the cost
economically.
The cost of the recycled plastic now, if you want to buy bales of recycled material, it's pennies on what it used to be in the past, right? So nobody wants to recycle it, clean it, bale it, get it ready for transport if they're making $1 a ton. It costs them far more to go and pick up the material than it is to sell it. That, yeah.
There's no incentivization to recycle it.
And that's part of the problem why we have stockpiles around the globe. I mean, Australia has a stockpile, I believe it's 6 kilometers long of material that's all baled, that they're looking solutions how to get rid of it. I've been to Nigeria recently, and I mean, there is a garbage dump that is larger than this campus, that's roughly about 25 feet to minimum high of just plastic material that's contaminated and been rotting there for years. Who wants to touch that, right? It's finding these technologies. And all that material will work its way down to the water one way or another, from rains, from people plowing or developing nearby or whatever the case may be. So it's got to be a technology solution, I think, because changing people's habits will take a long time. Everyone's interested in doing it. But the cost of doing it, as they were saying earlier, is far more expensive to do it. Who will get up every single time and wash that plastic plate before they put it into the recycle bin? If you go into any how do you say it? Sorry, I think in French and convert to English here. If you go into any shopping mall and go into a food court and just sit there and watch for 10 minutes, you don't see a single person take the plate or take a napkin and wipe it down before they put it in. They just go food and everything and just right in and off they go.
There is a positive note in terms of, at the Mascaro Center, 2 of the directors were just awarded a convergence grant to look at the circular economy when it comes to things like plastics, right? So I think there's more research that's looking at how do you actually create the circular economy around plastics.
We're trying a project in India where we're doing that, where we're implanting some equipment and we're paying the people that pick up the cardboard on the streets and so forth, we're basically paying them to bring plastic to us. So all we're asking them to do is pick up plastic, no cardboard, just bring us plastics and we'll pay you on a per pound basis and we'll see where that goes. And hopefully that'll give them some money. Our goal is to have the children stop going through the dumps and picking up plastic, that the families can make enough money with the adults doing it and not necessarily having to take the children to go out and do this. Let them go to school and learn and go forward. But that's way too early to say if it's going to work.
So maybe at this point we'll open up questions to the audience and also panelists themselves if there's something you want to ask your fellow panelists. So the 2 mics there in the aisles for any questions.
Hi, I'm Jackie Nunez, Plastic Pollution Coalition. Great talks, I really appreciate it. And David, I was loving how you were invoking biomimicry and talking about these systems. I'm not a scientist. I'm a communicator. I work with children a lot. I started the Last Plastic Straw movement, and I use it as a tool to talk about the greater problem of plastic pollution. One of the things that really frustrates me with this conversation, I took a 3-day recycling class at Ecology Center in San Francisco, and the whole premise for me taking this class was to find out what are we doing with plastics. And on the 3rd day, after lunch, we still haven't touched on plastics, and I realized why. I was just so devastated to see the system that we had for recycling. And I argue that plastic never was recyclable. It's not disposable. So, and I do see a redesign. It's an incredible material, but it frustrates me to have to go through these processes trying to think about it, and how to, in policy, what is recyclable, what's not, when it's not recyclable. It never was, and we're downcycling it once at best, but it doesn't fit the true definition of recyclability. So when we talk about redesign, the one thing that gave me hope is when I learned about metals, and maybe you guys can shed some light into this, but when metals first came on the scene, we thought we would never recycle metals either. There were so many formulations of metals with the industrial age. But then the war happened, and we were forced to streamline our processes. When you talk about regulation, I just feel that they need a timeout. They are unregulated, running unchecked, and it was just devastating to hear from Chris about these other plastics that they're, with these other combinations of chemicals that they're doing that's just, out of control. So I do think that there's space for regulation, but the only thing that gave me hope was when I learned about metals, that they were forced to streamline their processes for the war so that we could take metals back and recycle it and be able to take it back. And I just feel that this is where we're at. It's the science, but it's also regulation. And if you guys have any insight on that, but I just feel like we're just going in circles trying to find solutions when, the solutions are much more producer accountability and having to have stricter regulations. And I think that's what you guys are getting at, but it's not going to be this miracle new material. It's just going to be like, let's get a handle on this stuff and stop this flowing into our environment. But we really need some, restrictions put on this. So if you had any other insights on that, but.
I mean, I agree with you in terms of the solution is multiplexed. It's multiplexed. I don't think that, it's just a technology, because with the technology, there's always a rebound effect. And you never realize the full efficiency of your new technology, because those resources are allocated other ways, or et cetera, right? If you reduce my bill, at my house to 1%, well, that may mean that, okay, I might extend myself to use more as and rebound in terms of my use, or grow my use. So I think it's culture. I think it is policy. I think it is the necessity now is kind of helping to catalyze a lot of these movements on policy, on technology, and things like that. One of the things I'm looking forward to, or I like to see, is just a lot of the smaller successes. right? Because these successes that happen in a very, very local environment kind of inspire and help translate to others. What I see, right, with the biggest thing is, everything, when you're talking about a region, you're talking about a city, that's an ecosystem where people can actually interact and interact with frequency. Right? You and I probably don't interact with frequency with our senator at the federal level. Right? And so I think much of the, some of the successes are coming out in very regional ways. Like our problems in Pittsburgh are not the same as the problems in Boston or necessarily in California. They probably overlap, they probably rhyme in a variety of different ways, but they're not always the same. Right? And so I agree with you in terms of it's multiplex.
Well, and the other thing I want to touch on too, because I keep hearing how cheap plastic is, but there's also this false narrative on that because it's heavily subsidized. So if it wasn't subsidized like it was, and also it's also the feedstock is like, I like to say it's basically the toxic waste of the petrochemical industry is the feedstock for plastic. So we are tasked to deal with the toxic waste of that, and it's being transferred to our communities, and we're wrapping our food in it, feeding our babies out of it, and. It's mind-boggling, but I just feel like, this conversation about cheapness of plastic is almost maybe with the plastic life cycle, finding the true cost of what it really is.
I don't think that we pay the environmental cost, right? Like we don't. It's an externality that's not accounted for sure.
Health, health environment. Thank you.
I think it's one of our major environmental problems overall is we don't pay for
there's many things that are unaccounted for.
Carbon dioxide's problem, and plastic is problem, and all sorts of things.
There's a lot.
Yeah, go ahead.
Me again. There is the end producer responsibility concept, which is starting to take hold, which is that if you produce something that has costs, you should be factoring in the costs of dealing with it all the way through its life cycle. And so I'm curious if you all are starting to incorporate that idea in your thinking. And again, it's getting at this externality, and how do we start to shift it back to the users and the producers, because it really isn't fair that municipalities and governments are being forced to deal with a problem that needs to be addressed at its source. And I think that's a really critical piece of the action that we probably need to take in order to really start to address the plastic issue.
Well, in actuality, it's not the municipality that's paying, it's you that's paying for it through your taxes on these recycling programs or curbside collection programs. And as I try to push around the globe is, there's got to be a cradle to grave responsibility for the material. Now, if somebody in the local region is making a product, selling a product, can they not work with the recycling groups to reappropriate back that product? They do factor in a cost of recycling, but if it's just being put into a land dump, where's that money going? Who has access to those funds in a bottle exchange program or whatever the case may be? So it's got to go further than that. And if you know a supplier or a manufacturer is making these goods and it's consistently going out into the waste stream and you're seeing it on the streets and the rivers and so forth, shouldn't there be a responsibility of that company to get directly involved in changing that packaging? Not just picking it up, but changing it, looking at the next generation of packaging to go forward. There's companies like Unilever, they've jumped on board to do some of that. P&G and some other firms have done that. PepsiCo has jumped on board to do things like that, to look at the next generation of packaging. But there's just so much to do.
I mean, I think there's lots of different ways this can go in terms of your policy, and I think whether it's at the local, at the city, at the regional, at the federal level, like I think it might be a portfolio of responses for how to ensure that responsibility. What I'd like to share is maybe some of the positive successes that I've seen. So traceability is a very, very big important thing. And if you look at food, where a lot of packaging comes from, many people are demanding a lot more traceability. If you look at some of the food surveys, what they're looking at is local sometimes is superseding sustainable. And the reason why is because they intuit that local is sustainable. It's local, helping out the local job, dollars staying in the economy. The idea is that they're not necessarily a big firm using large industrial practices. And so when those things take hold, normally the dollars follow. Another good example is what REI did with REI Opt Outside, right? It turns out like they didn't do anything on that Black Friday, but they gained such a push that it ended up, I don't know, I think it's $8 million that they ended up getting later on because of the fact that they stood for something. So these are positive things that I see in terms of how companies or agents or different people are changing the game without necessarily moving the big ship, moving the Titanic. So I see that as interesting and inspiring.
It's Deanna. I feel like I just need to say something. Recycling is a really cool idea, but you may have higher recycling rates and maybe there's more of an infrastructure in Canada. I don't know. But in the United States, we really don't have infrastructure to support it. In fact, in California, they just closed the one plant that took number 5 is closed now. And it couldn't exist without subsidies, and finally they just, so the fact that right now that 1 and 2 have some value still, it seems like a farce to me, honestly.
Well, it is. It's window dressing, and that's exactly that. It's like when you go to the airport and you go through the metal detector and the X-ray machine. That's just window dressing to make people feel nice and safe and calm. And these recycling facilities put in by the municipalities. Sorry, it's not a theory I'm running or anything. It's just a general comment. But these recycling firms, again, if they can't sell the material can't be used, then why do we bother picking it up and spending all that additional fuel, manpower, adding all that additional carbon into the air to do all this exercise, to truck it back to a sorting center that we sort it all out, take the other stuff and bail that and move that off to somewhere else and take this and move that over. You're spending a lot of energy. I call it a make-work project, and it's not benefiting anyone, and it's just confusing the population because, as you say, 3 to 5 years down the road, the recycling plant's closed because it doesn't make any sense, or the municipality doesn't want to subsidize the collection of it. It's got to be the manufacturers of these materials that got to put money into a fund to be able to start addressing the bulk of the material that they're creating as waste.
I think it's not just the manufacturers, though. I think it's also all of the corporations and companies that choose those materials to package their food and beverage and products in.
Agreed.
And so that's EPR.
Yeah.
But anyway, yeah, thanks.
Yeah.
Why don't we do 1 and 1, and that's all the time we have. Go ahead.
Hello, this is Boya from MIT. I have a question for David. I've definitely heard a lot of great things about University of Pittsburgh has a really strong cohort of scientists on sustainability. So I really like how you mentioned using green engineering and green chemistry principles for informing future plastic design. And from what I have read most of assessing the sustainability matrix of plastic material has really focused on the source of the polymers. So bio-based materials has a much higher, rated as a much higher sustainability-wise compared to petroleum-based. But we also heard a lot of things about challenges in recycling them, which is unsustainable. So I'm curious, what do you think of the appropriate matrix of sustainability that we should consider in terms of design rules and design matrix that we should really choose that is appropriate for plastic materials?
Yeah, that's a good question. I agree with you on the, it really is at the source. I mean, Sam Mason, who was doing the microbeads one, she told me a story. She says, if you walk into your house and, it's all flooding, you're not gonna get towels. You're gonna go to the faucet and turn it off. So I think you're right that it's at the core. When it comes to what the design value matrix should look like in terms of what materials, again, sustainability is extraordinarily contextual, right? And it's contextual in the terms of what's good in California may be very, very different because of the local industry base and the local economy. We're kind of in the Rust Belt, if you will. And so which plastics, each one has to be looked at in context. And I know it seems complex, but ultimately I say that because sustainability is really a design value. Right, that's what it is, and it's your design should just be an expression of those values. So PLA could be really, really good over in Pittsburgh, right? It could be, hey, this is good. We're going to source it from here because we have $135 billion in agricultural assets. Great. I don't have the complete answer, and I don't know that it's actually a single answer for plastics. I do think that single use, right, I do think it will start to fade more and more as our cultural shifts and wants to see a different expression in design.
Hello, my name is Jan. I'm at MIT postdoc. My background is bioplastic manufacturing, and indeed it is not, the perfect material that will save the world, as some people realize later on. But anyhow, I have two other questions, because now I work on general plastics and I give lectures on how to design sustainable materials, and I consult some friends on how to make a sustainable packaging for their protein bar. And it's not so easy to come up with the perfect answer. One question would be, in developing countries, where much of the plastic waste might come from because they don't have infrastructure, what do you think will be the most likely way to help with the plastic problem? Will it be consumer behavior change, or will it be a very cheap recycling technology, or will it be bioplastic? And the second question is, why would you, I heard sometimes that pyrolysis is being hated on, but pyrolysis is actually the only chemical process at the moment that you can use for polyolefins that have no ester bonds, for example, to be chemically recycled to raw material that you can actually polymerize into a new polymer. It's not a new polymer, it's a recycled polymer then still, right? So that should be, I thought that should be a technology to facilitate circular plastic economy.
Well, on the pyrolysis question, I mean, if you take a look at, if you're looking at the gasification side, or if you're looking at bringing it back to the base polymer, first of all, the energy consumption requirement just to be able to convert the material back far offsets any gains that you're going to have in the recycling of that material. That's number one.
Right. For that, isn't it then still a sort of a pseudo future technology if you could supply that energy with renewable energy, because you need a whatever technology to turn an old material into a new one?
It's a very high cost operation system, let alone just the energy requirement for that. The gases that are required to go through, the maintenance of the equipment, how much material can you feed through the pyrolysis system to be able to go back to the base polymer? And then when you do make that base polymer, what are you going to do with it? You're going to make more plastic. Let's find something that uses it in another method. Can we generate some energy with it? Can we create something that we can use that's not going to be toxic to the environment afterwards? And pyrolysis is a technology that's out there. A lot of people have invested a lot of money. There's some plants in the UK. There's a couple of plants in Canada. There's one literally about 5 miles away from my home that I stop into on a regular basis to see what's new, what's going on. And it's, in my opinion, it's just not commercial sense to make that thing run. It's very high cost, very complicated system, a lot of maintenance. You can't just take anyone and have them run this equipment. You want something that you can implement globally, around the globe. Educational levels, skills of individuals out there are different around the globe. How do you implement something like that? That is a great lab technology, but implementation globally?
Yeah, for me, I think I'm gonna go back to context, right? So for me, I'm not against pyrolysis. I'm not against necessarily plastics. It's always in context. And so, for example, like a single-use plastic that I still think is valuable is in the medical field. If you're going to approve something through the FDA, they prefer single-use because they don't want to see it as a vector of disease or contamination. I don't necessarily want to reuse like syringes, right, for patients to patients. And so when it comes to those plastics, if there is an energy cost for it, perhaps it's adding some sort of value like that. So for me, the answer when somebody poses a question is, it depends, right? It really, really does. It does depend, right? It's how engineers answer everything. Yeah. And so I think, for pyrolysis, give me the context, and then I think there can be value in a variety of different ways. But the medical field, for example, is one in which you think about recycling of plastics, reuse of plastics, and they do that for actually human health, reasons. So.
What about the other question, the developing country question?
Oh, I'm sorry.
What would be? What do you guys think is the way to change for better in terms of plastic in the developing countries? Is it consumer change?
Yeah.
or is it plastic technology that we in the Western world need to develop for them? What do you think?
This is just my opinion. If I had the lever and you gave me a lever for consumer behavior, I'd take that. And because culture eats strategy for breakfast all day, right? And so if people decided and changed their habit, like, our lives change when our habits change. As soon as you change your habits, everything falls into place. So if you had that to change habits, some people do it by design, some people do it by actual, changing habits and going through it. But yeah, that one's a big one. Policy, technology, those are all byproducts of whatever the culture is. And the culture is your values. So if that's something we value collectively, everything else is simply a byproduct of that. And this is just my opinion. Yeah.
If people are poor
science
and
point of view, we might want to get back to your question. How do we better understand what's out there on a broad scale? What sort of future do you see for large-scale monitoring, for really getting a better feel for what is really there?
Every time the current operation that's out there that's collecting some plastic off the surface, I keep saying, please don't throw it out. I keep saying, please, please, somebody, I hope, and I don't know, I'm too far removed. I'm just begging and hoping, and I keep meaning to send an email to somebody to say, I hope you're archiving and labeling every single one of those pieces. Because the more that we understand what was recovered and what is there is incredibly invaluable, because we can start to see what is the relative percentage of each one of those products that we're recovering, and then compare it to what is the input term that we're trying to get a feel for. So I look at those admirable and interesting ways to recover plastics that are ongoing. I see them as a victory that we're removing plastic from the deck, but I see them as an unbelievable scientific resource. And that's low-hanging fruit to me. If they get thrown away or turned into diesel, no offense, I would cry. What a library of data. Oh my gosh. So that would be, and if my low-hanging fruit would be, although it's not a big long-term win, but if we're looking for victories when there's not a lot of research dollars out there, I'd go to every beach and find those beaches where there's a lot of plastic, especially in the low-income areas, and get it off. I mean, you're gonna win there. It's not the biggest win in the long term, but at least it's a win.
If it's really short, go ahead.
Just one thought that I recently had about incentivizing is the cases of the recent public nuisance lawsuits. So the suits regarding the opioid manufacturers is pretty startling that has worked. And then there's also a whole huge series of recent lawsuits against Monsanto by municipal water organizations for their costs in terms of meeting their NIPD's permits for stormwater discharges that are ongoing. So let's bring in the lawyers. Kidding, but I mean, it struck me as kind of these public nuisance lawsuits have recently been pretty successful, and I think the key to that is really defining what is a nuisance. So.
There was a lawsuit that was started in Canada, in Ottawa, about 3.5 years ago to a Canadian petrochemical company that supplied plastic firm the materials to make it. And their argument, which they won in court, was if we make the car and the car is there, but you drive it into a person, who's responsible on it? And they're saying we make the product, but if it's not disposed of properly, it doesn't become our responsibility. And that's where in Canada it made a lot more emphasis to the situation of asking companies now to put money into a fund to assist in the cleanup. So they take a percentage of their profits that would be put into a fund that's used to do plastic cleanup, beach cleanups, remediation, stuff like that.
All right, I think that we're already over time, so please join me in thanking our panel on the plastic life cycle.